the moon will never be a human home. It is the closest world to ours, hanging just 250,000 miles above our heads, and yet it might as well be a grave. Because for all the beauty we see when we look up at that pale light in the night sky, for all the poetry we have written about it, for all the dreams we have dreamed about building cities on its surface, the truth is painfully simple. The moon does not want us there. It never did. And the science behind that rejection is so thorough, so absolute, that once you understand it, you will never look at the moon the same way again. But here is the thing. You probably already sense that something is wrong with the dream of living on the moon. You clicked on this video because some quiet part of your mind has been asking the question, if the moon is so close, if we already landed there more than 50 years ago, why have we not gone back to stay? What is it about that silent silver world that keeps pushing us away? Well, settle in, get comfortable. Let the sound of this voice wash over you the way starlight washes over the lunar plains. Because tonight, we are going to take a long, slow, deeply honest look at every single reason the moon will never be our second address. And some of what you are about to hear will genuinely surprise you. Not because it is hidden, but because nobody ever stitches it all together in one place. Nobody ever lays out the full picture. Tonight, we do. Let us start with something most people never think about. The air, or rather, the absolute and total lack of it. When you step outside your front door right now, whether it is morning or evening, whether you are in a city or a field, you are swimming in an ocean of gas. Every cubic centimeter of space around you contains roughly 10 quintillion molecules. That is a 1 followed by 19 zeros. Those molecules are constantly bouncing off your skin, pressing against you from every direction, filling your lungs, keeping the water in your blood from boiling, and shielding you from the vacuum of space. You do not feel this pressure because you grew up in it. Your body was built for it. Every cell in your body expects it. It is like asking a fish if it notices the water. Of course not. The water is everything. Now imagine removing all of that. Every single molecule. Imagine replacing that thick, warm, life-giving ocean of air with nothing. Not thin air, not cold air, nothing. That is the moon. The lunar surface sits in a vacuum so extreme that it makes the best vacuum chambers on Earth look crowded. Each cubic centimeter on the moon contains about 20,000 molecules. Compare that to the 10 quintillion on Earth. The difference is so vast that calling the moon's envelope an atmosphere is almost a joke among scientists. They do not even use the word atmosphere. They call it an exosphere. A surface boundary exosphere, to be precise. It is a technical way of saying there is almost nothing there. How empty is it? Tired of waking up at 3 a.m. because your sleep video ended? Cosmic Drifts Beyond the Stars plays for hours. No ads, no interruptions, no reaching for your phone. 5 full night sleep experiences, one-time purchase. Begin now at mycosmicdrift.com. When NASA sent instruments to the moon on the Apollo 14 mission, they measured the gas pressure on the surface. During the daytime, when the sun heated the ground and released trapped gases from the soil, the pressure was about 10 to the minus 10th torr. At night, after the surface cooled, the pressure dropped even further, to about 10 to the minus 12th torr. For comparison, the pressure at sea level on Earth is 760 torr. The moon's daytime pressure is roughly 10 trillion times lower than what you are breathing right now. And at night, it drops another 100 times below that. The entire gaseous layer surrounding the moon has a total mass of about 25,000 kilograms. That is about the weight of 5 elephants. The entire atmosphere of an entire world weighs less than a small herd of elephants. Let that sink in for a moment. And here is something most people do not know. The moon was not always this barren. About 3.5 billion years ago, the moon was volcanically active. Lava was pouring across its surface, and those eruptions released gases into the space above. For about 70 million years, the moon actually had a real atmosphere. Not a thick one like Earth's, but a real one. Gas molecules collided with each other. There was pressure. There was something like weather. But then the moon's magnetic field died, and without that invisible shield, the solar wind stripped every last molecule away, particle by particle, over millions of years. What remains today is essentially nothing. The moon tried to have an atmosphere once. It held on for tens of millions of years, clinging to whatever gases its volcanoes could provide, building something that might have been the beginning of a real envelope of protection. And then the solar wind came, and particle by particle, molecule by molecule, the universe said no. So what does this mean for a human being standing on the lunar surface? What would happen to your body if your spacesuit failed and you were suddenly exposed to this near-perfect vacuum? The answer is not what Hollywood tells you. You would not explode. Your skin is far too strong and flexible for that. Human skin is the largest organ in your body, and it acts like a natural pressure suit. It stretches, it holds, it contains. But what happens inside that skin is another story entirely. Within the first second, you would feel a strange coolness on your exposed skin as moisture began to evaporate. The water on the surface of your eyes, the sweat on your forehead, the saliva on your tongue, all of it would begin to boil. Not because it is hot, the opposite. In a vacuum, the boiling point of water drops dramatically. At normal body temperature, water exposed to vacuum turns to gas almost immediately. This process is called ebullition, and it is one of the most unsettling things that can happen to a human body. We know this is not just theory because it has happened. In 1966, a NASA engineer named Jim LeBlanc was testing a spacesuit prototype inside a massive vacuum chamber at the Johnson Space Center. During the test, the pressurized air hose connected to his suit accidentally disconnected. Within seconds, the pressure inside his suit plummeted. As he stumbled backward, he felt the saliva on his tongue begin to bubble. That was the last thing he remembered before he lost consciousness. His colleagues rushed to repressurize the chamber, and he survived. But that detail, the bubbling saliva, that tiny sensory memory, tells you everything you need to know about what vacuum does to the human body. It starts stealing your water the moment it gets a chance. Your body would swell, not like a balloon popping, but like a slow, awful inflation. The water in your tissues would turn to vapor, pushing your body to roughly twice its normal volume. Your circulatory system would struggle. Bubbles of nitrogen would form in your muscles and bones, exactly like the bends that scuba divers experience when they surface too quickly. And all of this would happen while you were still conscious. Because here is the truly terrifying part. You would not black out instantly. Studies and real-world accidents have shown that a person exposed to vacuum retains some degree of consciousness for 9 to 11 seconds. You would have about 5 to 10 seconds of useful awareness to try to save yourself. After that, your brain would shut down from lack of oxygen. But those seconds would feel like an eternity. There is one critical thing you must never do if you are ever exposed to vacuum. You must never hold your breath. If you hold your breath, the air trapped in your lungs has nowhere to go. The pressure difference between the air inside your lungs and the vacuum outside would rupture your lung tissue, almost instantly. And worse than that, air bubbles would be forced into your bloodstream, traveling to your brain and causing a stroke. The instinct to hold your breath is exactly the wrong instinct. You must exhale. You must let the air go. And what about freezing? Surely you would freeze solid in the void of space, right? Actually, no. Not quickly, at least. This is one of the great misconceptions about space. Space is not cold in the way a freezer is cold. A freezer is cold because cold air molecules are constantly pulling heat away from your body through conduction and convection. In space, there are no molecules to do this. The only way your body can lose heat is through radiation, the same way a light bulb slowly cools down after you turn it off. And humans radiate heat at a rate of about 100 watts. Given the mass of a human body, it would take a very long time to freeze solid. You would be long dead from suffocation before the cold became a serious factor. In 1982, a technician working in a vacuum chamber was accidentally exposed to extremely low pressure, equivalent to about 3.6% of sea level atmospheric pressure. He spent a full minute in these conditions. His skin turned blue, his lips frothed, his lungs bled. And yet, after being rescued and repressurized, he made a full recovery. This tells us something remarkable and frightening at the same time. The human body can survive brief vacuum exposure and recover completely. But the experience is brutal, and the window for rescue is measured in seconds, not minutes. Now, here is where the reality of living on the moon starts to become clear. Every single structure on the lunar surface, every habitat, every greenhouse, every laboratory, every corridor connecting one building to another must be an airtight pressure vessel. Think about that. On Earth, our buildings keep out rain and wind and cold. On the moon, buildings must keep out nothing, literal nothing. They must hold roughly 14.7 pounds per square inch of air pressure inside, while the outside is a vacuum. That translates to about 10 tons of force pressing outward on every square meter of wall. Every window, every door, every seal, every joint, every rivet must be absolutely perfect. Not mostly perfect, not 99.9% perfect, absolutely perfect. Because on the moon, a leak does not mean your heating bill goes up. A leak means everyone inside begins to die. And the moon is constantly trying to create those leaks. The lunar surface is bombarded by micrometeoroids, tiny rocks traveling at incredible speeds. On Earth, our atmosphere burns these up long before they reach the ground. That is what shooting stars are. On the moon, there is no atmosphere to stop them. They hit the surface at full cosmic velocity. A grain of sand moving at tens of kilometers per second carries enough energy to puncture a thin wall. So every habitat on the moon must not only hold pressure against vacuum, but also withstand a constant rain of microscopic bullets. And then there is the dust. But we will get to the dust shortly. For now, let us stay with the vacuum and consider something even more fundamental. Pressure containment is an engineering problem that humans have solved before. We build submarines that withstand crushing ocean pressure. We build spacecraft that hold air in the void. But there is a crucial difference between a submarine mission that lasts months and a permanent settlement that must last decades or centuries. Seals degrade, materials fatigue, and on the moon, there is a substance that actively attacks every seal, every gasket, every mechanical joint it touches. We will talk about that substance soon. For now, just understand that the engineering challenge of keeping air inside a moon base is not a problem you solve once. It is a war you fight every single day, forever, with no room for a single defeat. Let us leave the vacuum behind for now, though it will haunt every other topic we discuss tonight, because the missing air is not just an engineering problem. It connects to everything. It connects to radiation. It connects to temperature. It connects to dust. The moon's vacuum is not just one danger. It is the foundation upon which every other danger is built. And speaking of radiation, let us talk about the invisible storm that never stops. Right now, as you lie there listening to this, your body is being hit by radiation. Cosmic rays from deep space, particles from the sun, even tiny amounts of radiation from the ground beneath you and the walls around you. But the dose is incredibly small because you have two enormous shields protecting you. The first is the Earth's atmosphere, which is thick enough to absorb and scatter most incoming radiation before it ever reaches the surface. The second is the Earth's magnetic field, an invisible force field generated by the churning molten iron in our planet's core. This magnetic field, called the magnetosphere, extends tens of thousands of miles into space, deflecting charged particles from the sun and from deep space the way an umbrella deflects rain. The moon has neither of these shields. It has no meaningful atmosphere, as we just discussed, and it has no global magnetic field, not anymore. Billions of years ago, when the moon was young and its core was still molten and churning, it generated its own magnetic field. Scientists have confirmed this by studying the magnetism locked inside Apollo rock samples. The moon had a magnetosphere from roughly 4.25 billion years ago until about 2.5 billion years ago, with its peak strength occurring around 4 billion years ago. During that time, the Earth and the moon actually shared connected magnetic fields, forming a kind of double shield against the young sun's violent outbursts. But the moon is small, much smaller than Earth, and small worlds cool faster. As the moon's interior solidified, the churning motion that generated its magnetic field slowed and eventually stopped. By about 1.5 billion years ago, the moon's magnetosphere was completely gone. And without that shield, the solar wind began to strip away whatever thin atmosphere the moon had managed to hold on to. The result is what we see today: a dead magnetic field, a dead atmosphere, and a surface that is completely naked to the radiation of the cosmos. There is a poetic detail in this story that deserves a moment. Scattered across the lunar surface, there are strange bright and dark swirl patterns. They look almost like abstract paintings, and scientists call them lunar swirls. The most famous one is called Rhina Gamma. These swirls exist because in certain places, the moon's ancient magnetic field left behind small remnant patches of magnetism in the crustal rock. These patches are tiny, ranging from a few kilometers to a few hundred kilometers across, and they create miniature magnetic bubbles that partially deflect the solar wind. In the areas protected by these bubbles, the ground stays brighter because the solar wind cannot darken it through chemical reactions. Just outside the bubbles, the surface is darkened by radiation exposure. The result is a pattern that scientists sometimes describe as the moon's tan lines. The moon is literally showing you where its ancient shield still offers a faint whisper of protection, and where the radiation has been beating down uninterrupted for billions of years. But these tiny patches cannot protect a human being. They are remnants, echoes. The real shield is gone. So what exactly is raining down on the lunar surface? There are 3 main types of radiation that a person on the moon would face, and each one is dangerous in its own way. The first is galactic cosmic rays. These are the heavy hitters. They are the nuclei of atoms that have been stripped of all their electrons and accelerated to nearly the speed of light by the shockwaves of ancient supernova explosions somewhere in our galaxy. Imagine the core of a hydrogen atom, or a helium atom, or even an iron atom, moving so fast that it carries tremendous energy. That is a galactic cosmic ray. They are composed primarily of protons, about 87%, with about 12% being helium nuclei, and the remaining 1% being heavier elements like carbon, oxygen, and iron. These particles are so energetic that they can pass straight through a spacecraft hull, straight through a spacesuit, straight through your skin, and straight through your cells, leaving a trail of ionization damage in their wake. Your DNA, the very blueprint of your body, can be shattered by a single one of these particles. And here is something that makes this problem even worse. You cannot simply shield against galactic cosmic rays with thick metal walls. In fact, thin aluminum shielding, the kind used on most spacecraft, can actually make the problem worse. When a galactic cosmic ray hits an aluminum wall, it does not just stop. It creates a shower of secondary particles through nuclear reactions. Protons, neutrons, alpha particles, gamma rays, and other fragments spray inward like shrapnel. This secondary radiation can be just as dangerous as the original particle. It is one of the most frustrating problems in space radiation protection. The shield itself becomes a new source of danger. The second type of radiation comes from solar particle events. These are massive eruptions on the surface of the Sun, solar flares and coronal mass ejections that blast enormous clouds of charged particles out into space. Unlike galactic cosmic rays, which provide a constant low-level background, solar particle events are sporadic and unpredictable. They can happen at any time, and when they do, they flood the space between the Sun and the planets with high-energy protons. A major solar particle event can deliver a radiation dose large enough to cause acute radiation sickness within hours. We are talking about nausea, vomiting, organ damage, and potentially death. During the transit of the Mars Science Laboratory from Earth to Mars, 5 separate solar particle events were recorded. 5 events during a single trip. And that was during a relatively quiet period of the 11-year solar cycle. The Apollo astronauts were extraordinarily lucky that no major solar particle events occurred during any of their missions. If one had struck while they were on the lunar surface, with only the thin walls of the lunar module for protection, the consequences could have been fatal. The third type of radiation is secondary radiation, and on the Moon it takes on a unique and disturbing character. When galactic cosmic rays and solar particles slam into the lunar surface itself, they create cascading showers of secondary particles that spray back up from the ground. Neutrons are a particular concern because they are electrically neutral, meaning they cannot be deflected by any magnetic field, and can penetrate deeply into human tissue. So on the Moon, radiation does not just rain down from the sky, it also rises up from the earth beneath your feet. The very ground you are trying to stand on is radiating particles back at you. You are caught in a crossfire between the cosmos above and the soil below. Now, you might be wondering, how bad is the actual health impact? Let me share the most chilling piece of evidence we have. Only 24 human beings have ever traveled beyond Earth's magnetosphere. All of them were Apollo astronauts who flew to the Moon between 1968 and 1972. By the time a landmark study was published in the journal Scientific Reports in 2016, 8 of those astronauts had died. The researchers compared causes of death among 3 groups: non-flight, astronauts who trained but never went to space; astronauts who flew only in low Earth orbit, still protected by Earth's magnetic shield, and Apollo astronauts who traveled to the Moon, passing through and beyond the magnetosphere into open, deep space. The results were startling. Among non-flight astronauts, the cardiovascular disease mortality rate was 9%. Among low Earth orbit astronauts, it was 11%, nearly identical. But among the Apollo lunar astronauts, 43% of the deceased had died from cardiovascular disease. 43%. That is 4 to 5 times higher than the other two groups. And these were not unhealthy men. These were among the fittest, most rigorously screened human beings on the planet. They ate well. They exercised. They had access to the best medical care in the world. And yet, after spending just a few days beyond Earth's magnetic shield, they developed heart and blood vessel problems at an astonishing rate. To investigate the mechanism behind this finding, the researchers exposed laboratory mice to radiation doses, similar to what the Apollo astronauts experienced. 6 to 7 months later, the equivalent of roughly 20 human years, the mice showed significant and persistent damage to the cells lining their blood vessels. This kind of damage, called vascular endothelial dysfunction, is a well-known precursor to atherosclerosis, the hardening and clogging of arteries that causes heart attacks and strokes. The deep space radiation had altered the fundamental health of the cardiovascular system, and the alteration did not heal with time. Let that settle in for a moment. A few days in deep space. Just a few days. And the cardiovascular effects showed up decades later at 4 to 5 times the normal rate. Now imagine living on the Moon for years, for a decade, for a lifetime. The radiation exposure would be continuous, day after day, night after night, with no escape. The cumulative damage to the cardiovascular system, the nervous system, the immune system, the eyes, the DNA in every cell of the body would be staggering. And there is one more detail from the Apollo missions that is both beautiful and terrifying. Multiple astronauts reported seeing bright flashes of light during their journeys, even when their eyes were closed and the cabin was dark. These flashes appeared as streaks, spots, and brief bursts of white light. For years, scientists debated the cause. Eventually, they confirmed what was happening. Individual cosmic ray particles were passing directly through the astronauts' eyes, striking the photoreceptors in their retinas and creating the sensation of light where none existed. In some cases, the particles were passing through the visual cortex of their brains, triggering visual experiences from the inside out. Every flash was a single particle, born in the violent death of a distant star, traveling across the galaxy for millions of years, and ending its journey by threading through the brain of a human being floating between worlds. On Earth, you never experience these flashes because the atmosphere and magnetosphere absorb nearly all such particles before they can reach you. On the Moon, there is nothing to stop them. You would see these phantom flashes of light regularly, a streak across your closed eyelids as you try to sleep, a spot of brightness at the edge of your vision as you eat breakfast. Each one a gentle reminder that the universe is passing through you, one particle at a time. And each of those particles carries the potential to nick a strand of your DNA, to damage a cell in a way that will not become apparent for years or decades. Every flash is a dice roll. And on the Moon, you would be rolling those dice thousands of times a day for the rest of your life. You might also assume that when the Moon passes behind the Earth, entering the shadow of our planet's magnetosphere during the full moon phase, astronauts would finally get a break from the bombardment. After all, the magnetosphere extends far enough to theoretically shield the Moon, for about a quarter of its orbit. But recent research has shattered even that small comfort. A study using NASA's Themis and Artemis probes, which orbit near the Moon, found that during periods of gusty solar wind, the magnetosphere's protective tail does not stay still. It flaps. Like a windsock in an unsteady breeze, the magnetosphere's tail can swing sideways, exposing the Moon to the full force of the solar wind and the turbulent, energized particles of the magnetosheath, the chaotic boundary layer between the solar wind and Earth's magnetic shield. So even during the full moon, when you might expect protection, the shield can suddenly swing away and leave you naked. There is no safe time on the Moon. There is no safe place. The radiation is always there, coming from every direction, and every attempt to shield against it creates new problems. This is not a challenge that will be solved by thicker walls or better technology in the near future. It is a fundamental feature of a world that has lost its magnetic heart. There is one more detail about the Moon's relationship with Earth's magnetosphere that is worth lingering on, because it shatters the last remaining hope for natural radiation protection on the lunar surface. Once each month, during the full moon phase as seen from Earth, the Moon passes through the long tail of Earth's magnetosphere. This tail extends far beyond the Moon's orbit, stretching hundreds of thousands of kilometers into space on the side of Earth facing away from the Sun. In theory, this passage should provide the Moon with a few days of magnetic shielding each month, a brief respite from the constant radiation bombardment. For years, some scientists hoped that this periodic sheltering might reduce the cumulative radiation dose for future lunar residents. But data from NASA's Themis and Artemis spacecraft, which orbit in the vicinity of the Moon, revealed that this hope was largely unfounded. The magnetosphere's tail is not a stable, reliable shield. It is dynamic. It responds to changes in the solar wind, the way a flag responds to gusting wind. When the solar wind is steady, the tail points more or less straight away from the Sun, and the Moon passes through it cleanly. But when the solar wind gusts or shifts direction, the tail flaps sideways, sometimes dramatically. During these fluctuations, the Moon can be swept out of the protective tail and into the magnetosheath, the turbulent boundary layer between the solar wind and the magnetosphere. The magnetosheath is not a sheltered zone. It is a chaotic region filled with heated, compressed plasma and energized particles. Being in the magnetosheath can actually increase radiation exposure rather than decrease it. The research showed that during periods of active solar wind, the magnetosphere's tail can oscillate so violently that the Moon spends only a fraction of its theoretical transit time actually inside the protective region. The rest of the time, it is either in the magnetosheath or exposed directly to the solar wind, so the monthly passage through Earth's magnetic tail, which once seemed like it might offer a few days of natural protection, turns out to be unreliable at best and potentially counterproductive at worst. This finding closed one of the last remaining doors to natural radiation mitigation on the Moon. There is no global magnetic field, there is no atmosphere, and the one external shield that might have helped, Earth's own magnetosphere, cannot be relied upon. The Moon exists in a radiation environment that is essentially unmitigated by any natural force. Everything between the cosmic radiation and the cells of your body must be provided by human engineering. And as we have discussed, human engineering on the Moon faces its own formidable set of challenges. But radiation, as devastating as it is not the most immediate physical threat on the lunar surface. That distinction belongs to something far more humble, something you can hold between your fingers, something that seems almost absurdly simple compared to the cosmic forces we have been discussing. It is the dust, the lunar dust, and it is, without exaggeration, one of the most insidious substances any human being has ever encountered. The surface of the moon is covered in a material called regolith. It is not soil in the way we think of soil on Earth. There are no organic compounds in it, no decayed leaves or worm castings, no microbes breaking down nutrients. It is ground up rock, plain and simple. But the way it was ground up makes all the difference. On Earth, rocks are broken down by wind, water, and chemical reactions over thousands of years. These processes round off sharp edges, smooth out jagged surfaces, and create particles that are relatively gentle to the touch. Think of sand on a beach. Those grains have been tumbled by waves and worn smooth by time. They slip through your fingers without cutting you. They are soft in the way that only deep geological patience can produce. On the moon, there is no wind, there is no water, there is no chemical weathering. The only force breaking down rocks on the lunar surface is violence. For billions of years, micrometeoroids have been slamming into the moon at speeds that defy imagination, tens of kilometers per second, pulverizing rock upon rock upon rock. Each impact vaporizes material, melts it, and shatters it into fragments that range from boulders down to particles smaller than a red blood cell. And because there is no wind or water to smooth the edges of those fragments, they stay sharp, permanently sharp. Imagine taking a piece of glass and smashing it with a hammer, then smashing the pieces again and again, until you have a powder so fine you cannot see the individual grains. But each grain, under a microscope, still has the edges and points of broken glass. That is lunar regolith. Scientists who have studied Apollo samples under electron microscopes have categorized the particles into several types. There are glassy beads, tiny spheres of material that melted during impacts and cooled into round shapes during flight. There are angular shards, glassy fragments with sharp edges formed from the crushing of larger pieces. There are vesicular particles, grains filled with tiny holes left behind when solar wind gases escaped from the material. And there are agglutinates, loose collections of particles welded together by impact glass. All of them share one common trait. They are abrasive, they are clingy, and they are everywhere. The clinging is not just a matter of the particles being small. There is something else going on. The lunar surface is constantly bombarded by ultraviolet radiation from the sun and by charged particles from the solar wind. This bombardment gives the dust particles a strong electrostatic charge, similar to what happens when you rub a balloon on your hair. The charged dust clings to everything it touches. Spacesuits, tools, equipment, visors, cameras, solar panels, anything that comes near the surface gets coated. And unlike static cling on Earth, which can be dissipated by humidity in the air, there is no moisture on the moon to neutralize the charge. The cling is permanent until the charge is somehow removed. The Apollo astronauts discovered all of this the hard way. Every single one of the 12 human beings who walked on the moon reported problems with the dust. Harrison Schmitt, the geologist astronaut on Apollo 17, was the first to give it a name that stuck. He called it lunar hay fever. After his moonwalks, he experienced sneezing fits, nasal congestion, sore throat, and watery eyes. Other astronauts reported similar symptoms. The dust got everywhere. It coated their spacesuits so thoroughly that brushes and vacuum cleaners could not fully remove it. When they came back inside the lunar module and removed their helmets, the dust that had hitched a ride on their suits was released into the cabin air. They breathed it in. It irritated their eyes and their airways, and it had a distinctive smell. Multiple astronauts described it as similar to burnt gunpowder or spent fireworks. Gene Cernan, the commander of Apollo 17 and the last human being to walk on the moon, was blunt in his assessment. During his technical debriefing after the mission, he said that dust was probably the greatest obstacle to normal operations on the moon. He believed that other physical, physiological, and mechanical problems could be overcome. But the dust, he said, was something else entirely. This was not the grumbling of an inconvenienced explorer. This was a warning from a man who had been there, who had felt the dust infiltrate every system and every surface, who understood in his bones that this fine grey powder was a threat that dwarfed almost every other challenge. And the damage was not limited to human health. The dust ate away at the outer layers of spacesuit boots, wearing through materials that were designed to withstand the harsh conditions of space. It destroyed the vacuum seals on sample containers, containers specifically designed to preserve the lunar environment. It clogged mechanical joints and mechanisms. It scratched visors and gauges. And all of this happened during visits that lasted only hours. A few hours of moonwalking, and the dust had already begun to degrade equipment designed by the best engineers in the world. Now imagine a permanent settlement. Imagine people living on the moon for months, years, decades. Imagine going outside every day to maintain equipment, to conduct research, to repair infrastructure. Every excursion would bring more dust inside. Every airlock cycle would let a little more past the seals. Over time, the interiors of habitats would become contaminated. Air filtration systems would be under constant assault. Mechanical systems would slowly grind down. And the people breathing that filtered air would be inhaling trace amounts of a substance that is unlike any dust on Earth. Because here is the truly frightening thing about lunar dust. It is not just abrasive. It is toxic. The regolith contains more than 50% silica oxide. On Earth, silica dust is one of the most dangerous occupational hazards known to medicine. Miners, stonecutters, and construction workers who are chronically exposed to silica dust develop a condition called silicosis, a progressive and incurable lung disease. Silicosis causes inflammation, scarring, and eventually destruction of lung tissue. It cannot be reversed, and the silica in lunar dust is not the rounded, weathered form found on Earth. It is fresh, jagged, and chemically reactive. The sharp edges of the particles can physically cut into the delicate lining of the airways and the tiny air sacs deep inside the lungs, where oxygen exchange happens. The situation is made worse by the moon's low gravity. On Earth, when you breathe in a dust particle, gravity helps pull it down and out of your airways through a process aided by mucus and tiny hair-like structures called cilia. In the moon's 1/6 gravity, this clearance mechanism is much less effective. Particles that would normally be swept out of your lungs on Earth can penetrate deeper and stay longer in reduced gravity. Research has shown that in partial gravity, inhaled particles deposit more peripherally in the lungs, reaching deeper into the tissue where they can do the most damage. Scientists at the European Space Agency have noted that particles 50 times smaller than a human hair could remain suspended inside the lungs for months. Months. The longer a toxic particle stays in your lung tissue, the greater the chance of chronic inflammation, scarring, and ultimately disease. And the toxicity does not stop at the lungs. Research using lunar soil simulants, materials designed to mimic the properties of real lunar dust, has shown that prolonged exposure can destroy not only lung cells, but also brain cells. The damage appears to be driven in part by the generation of harmful molecules called hydroxyl radicals. These are reactive, oxygen species that attack cell membranes and DNA. The nanophase ion embedded in lunar dust particles, tiny spheres of pure iron on the nanometer scale, created by micrometeorite impacts, appears to play a key role in generating these radicals when the dust comes into contact with biological tissue. Secondary effects from lung exposure could also spread to other organ systems. Inflammatory signals from damaged lung tissue can enter the bloodstream and affect the cardiovascular system, the immune system, and even the brain. In animal studies, rats exposed to lunar dust simulants developed not only lung inflammation, but also signs of systemic oxidative stress and cardiac fibrosis, a thickening and scarring of heart tissue. The dust does not just hurt your lungs. It can reach out through your body's own communication networks and cause damage far from the original point of contact. NASA has established preliminary exposure limits for lunar dust, estimating that safe human exposure for a 6-month deployment is somewhere between 0.4 and 1 milligram per cubic meter of air. For context, that is far lower than the permissible exposure limits set for workers handling silica dust on Earth. The Moon's dust is considered more dangerous per unit of exposure than the industrial dusts that have been causing lung disease in miners and construction workers for centuries. Apollo 12 astronaut Alan Bean became accidentally exposed to regolith in 1970. He was one of the early cases that triggered decades of research into lunar dust toxicity, and the more scientists have studied it, the more alarmed they have become. Every new finding reveals another dimension of risk, another pathway for harm, another reason to take this powdery, grey substance very, very seriously. So when people talk about building a city on the moon, about families living there, about children playing in lunar habitats, ask yourself this: how do you keep a substance out of living spaces when it clings to everything with electrostatic force, when it is finer than flour, when it cuts through spacesuits and seals, and when breathing even tiny amounts of it can cause irreversible lung disease? The answer is that nobody knows. Not yet. And it may be that the answer is you simply cannot. The dust is the moon's immune system. It is how the moon fights back against any organism that dares to try to live on its surface. But even if we could somehow solve the dust problem, even if engineers invented perfect airlocks and perfect filters and perfect seals that the dust could never penetrate, there would still be a fundamental biological problem that no amount of engineering can fix, and that problem is gravity, or rather, the lack of it. The moon's gravity is roughly 1/6 of Earth's. If you weigh 180 pounds on Earth, you would weigh about 30 pounds on the moon. This sounds delightful. It sounds like freedom. You could jump 6 times higher, carry 6 times more, bounce across the landscape like a child on a trampoline. The Apollo astronauts loved it. They skipped and hopped and bounded across the surface with visible joy. And for a visit of a few days, the low gravity was wonderful. But for a permanent home, it is a slow-motion catastrophe. Your body is a machine that was built by evolution to function in one specific gravitational environment. Earth's gravity, at approximately 9.8 meters per second squared, is not just the background condition of your life. It is an active participant in your biology. Every system in your body, your bones, your muscles, your heart, your blood vessels, your inner ear, your eyes, your immune system, your brain, is calibrated to function under the constant pull of one full G. When you reduce that pull, everything begins to change, and not for the better. Let us start with bones. Your skeleton is not a static structure. It is a living, dynamic tissue that is constantly being broken down and rebuilt. Specialized cells called osteoclasts dissolve old or damaged bone, while other cells called osteoblasts lay down new bone material. On Earth, these two processes are kept in balance by the mechanical stress of gravity. Every time you stand up, walk across a room, climb a staircase, or simply sit upright, gravity pulls on your skeleton and the muscles attached to it, sending signals to the osteoblast to keep building. Without that gravitational stress, the balance tips. The osteoclasts keep dissolving bone at their normal rate, but the osteoblasts slow down because they are not receiving the signals that tell them new bone is needed. The result is a net loss of bone density. In microgravity, like on the International Space Station, astronauts lose roughly 1% of their bone density per month in weight-bearing bones like the hips, spine, and legs. 1% per month may not sound like much, but compounded over time. After a year, that is 12%. After 5 years, 60%. And here is the most alarming part. This loss is not reduced by vigorous exercise. Astronauts on the ISS exercise for 2 hours every single day using specialized resistance equipment, treadmills, and stationary bicycles. They work hard, and the exercise helps, but it does not solve the problem. The bones still lose density. The calcium that is stripped from the bones enters the bloodstream and is eventually filtered by the kidneys, where it can form painful and dangerous kidney stones. And the process of bone loss has been observed to continue unabated for more than a year. We do not know if it ever truly stops or if it just slows down to an undetectable rate. Now, the moon is not zero gravity. It is 1/6 gravity. So the question is, does 1/6 gravity provide enough mechanical loading to prevent bone loss? The answer, based on the best evidence we currently have, is probably not. A landmark study conducted on the International Space Station used a device called the Multiple Artificial Gravity Research System, which is essentially a small centrifuge that can spin mice at different gravitational levels while in orbit. Researchers compared 3 groups of mice. One group experienced microgravity. One group was spun at 1/6 g, simulating lunar gravity, and one group was spun at 1 full g, simulating Earth gravity. The results were clear. Bone density reduction under microgravity was mostly recovered by 1 full g, but 1/6 g only partially recovered it. The bones of the mice in simulated lunar gravity were better than those in microgravity, but significantly worse than those at Earth gravity. Lunar gravity helped, but it was not enough. A systematic review of the scientific literature reached a broader conclusion that is even more concerning. The review found that partial gravity exposure below 0.4 g appears to be insufficient to maintain musculoskeletal and cardiovascular conditioning over the long term. The moon's gravity is 0.16 g. That is less than half of the threshold that scientists believe is necessary. The moon simply does not pull hard enough to keep human bones healthy. The situation with muscles is similar, but has an interesting twist. That same mouse study found that lunar gravity was enough to prevent the outright wasting of muscle mass. The muscles of the mice at 1/6 g did not shrivel and atrophy the way they did in microgravity. But something subtler and potentially more concerning happened. The type of muscle fibers changed. In healthy muscles under normal gravity, there is a mix of slow-twitch fibers, which are used for sustained activities like standing and walking, and fast-twitch fibers, which are used for quick, powerful movements like jumping or sprinting. In microgravity, the slow-twitch fibers convert to fast-twitch fibers. The muscles lose their endurance capabilities and become configured for quick bursts. Lunar gravity prevented the mass loss, but did not prevent this fiber type transition. The muscles stayed roughly the same size, but changed their fundamental character. In full microgravity, the muscle losses are dramatic. Astronauts can lose up to 20% of their muscle mass in a single month, and muscle strength can decline by up to 30% in the same period. The losses hit hardest in the legs and trunk, the very muscles that are most important for standing, walking, and supporting the body against gravity. On the Moon, at 1/6 g, these losses would be less severe, but over years and decades, the gradual erosion of muscle quality, the slow conversion from endurance fibers to sprint fibers, would fundamentally change how the human body functions. A person who had lived on the Moon for 10 years would have muscles that looked superficially normal, but performed very differently from those of a person on Earth. And returning to Earth's gravity would be excruciating, if it were possible at all. But bones and muscles are just the beginning. The cardiovascular system also suffers under reduced gravity. On Earth, your heart works hard to pump blood upward against gravity, from your feet to your head. This constant effort keeps the heart strong and the blood vessels toned. In reduced gravity, the heart does not need to work as hard. It weakens. Blood pressure, regulation becomes impaired. Blood vessels lose their elasticity. On the ISS, astronauts commonly experience a condition called orthostatic hypertension, where standing up too quickly causes lightheadedness or fainting, because the cardiovascular system has lost its ability to respond to gravitational changes. This deconditioning begins within days of arriving in microgravity and persists for weeks or months after returning to Earth. The immune system is also compromised. Research has shown that microgravity weakens immune function, making astronauts more susceptible to infections and impairing their ability to heal from injuries. White blood cell function changes. The inflammatory response is altered. Wound healing slows. On a lunar base, far from advanced medical facilities, with limited surgical capability and no possibility of emergency evacuation to Earth, a weakened immune system could turn a minor injury or infection into a life-threatening crisis. And then there are the eyes. One of the most surprising discoveries of the space station era has been the prevalence of vision problems among astronauts. In microgravity, bodily fluids shift upward toward the head because gravity is not pulling them down toward the feet. This causes increased pressure inside the skull, which presses on the backs of the eyeballs and on the optic nerves. The condition is called spaceflight-associated neuro-ocular syndrome, and it can cause blurred vision, changes to the shape of the eyeball, and even permanent visual impairment. Some astronauts have returned from long-duration space station missions needing glasses for the first time in their lives. On the Moon, at 1/6 gravity, the fluid shift would be less extreme than in microgravity, but it would still be significant. A lifetime of reduced gravitational pull on the fluids in your body could gradually degrade your vision in ways that are not yet fully understood. There is something profoundly sobering about all of this. The human body did not evolve to live on the Moon. It evolved over millions of years to function under the specific conditions of Earth. 1 full G of gravity, a thick atmosphere, a magnetic shield, a certain amount of radiation, a specific composition of air, a particular range of temperatures. We are Earth machines, exquisitely tuned, beautifully adapted Earth machines. And when you take an Earth machine and place it in an environment that violates every single parameter it was designed for, the machine begins to fail. Not dramatically, not all at once, but slowly, steadily, and irreversibly. The bones thin, the muscles change, the heart weakens, the immune system falters, the eyes blur, the DNA accumulates damage, the lungs fill with glass. And the mind, which we have not yet discussed, begins to bend under a weight that has nothing to do with gravity at all. But before we talk about the mind, there is one more physical challenge we need to address. One that NASA has ranked as the single greatest technical obstacle to establishing a sustained human presence on the moon. And it is something so simple, so elemental, that it seems almost absurd to call it the biggest problem. But it is. It is the night. The moon rotates very slowly. One complete rotation takes about 27.3 Earth days relative to the stars, and because of the way the moon orbits the Earth, the cycle of day and night on the surface takes about 29.5 Earth days to complete. What this means in practical terms is both simple and devastating. At most locations on the moon, you get about 14 Earth days of continuous sunlight, followed by about 14 Earth days of total darkness, 14 days of unbroken night, no sunrise coming tomorrow, no light at the end of the tunnel for 2 full weeks, just darkness, absolute unrelenting silent darkness, and cold, a cold so extreme that it has no equivalent anywhere in human experience. During the lunar day, when the sun beats down on the surface with no atmosphere to scatter or soften its light, temperatures at the equator can reach approximately 127 degrees Celsius. That is 260 degrees Fahrenheit, well above the boiling point of water. The rocks bake. The dust shimmers in the unfiltered sunlight. Everything on the surface absorbs heat with nothing to moderate it. Then the sun sets. And because there is no atmosphere to hold on to any of that heat, no blanket of air to slow the cooling, the temperature does not just drop, it plummets. During the lunar night, surface temperatures fall to approximately minus 170 to minus 180 degrees Celsius. That is minus 280 to minus 292 degrees Fahrenheit. For context, the coldest temperature ever recorded on Earth at the Vostok station in Antarctica was minus 89.2 degrees Celsius. The lunar night is roughly twice as cold as the coldest place on our planet, and it lasts for 14 days. But it gets worse. At the lunar poles, there are craters whose floors never see sunlight, ever. These permanently shadowed regions are among the coldest places in the entire solar system. Temperatures there can drop to minus 238 to minus 240 degrees Celsius. That is minus 397 to minus 400 degrees Fahrenheit. That is only about 35 degrees above absolute zero, the theoretical temperature at which all molecular motion ceases. These are temperatures that approach the fundamental limit of cold in the universe. The total temperature swing on the moon from the peak of lunar noon to the depths of lunar midnight is approximately 300 degrees Celsius, over 500 degrees Fahrenheit. No natural environment on Earth experiences anything remotely close to this. And this swing happens not over the course of seasons, but over the course of a single lunar day-night cycle. Roughly every 29 days, the surface goes from furnace to freezer and back again. Every material on that surface, every structure, every piece of equipment, every habitat wall and window and seal must endure this thermal cycling repeatedly, month after month, year after year, decade after decade. The expansion and contraction caused by these temperature extremes puts enormous stress on materials, loosening joints, cracking seals, and fatiguing metal in ways that are difficult to predict and nearly impossible to fully prevent. On Earth, we take night for granted. The sun goes down, The temperature drops a few degrees, maybe 20 or 30 at most in the desert, and we put on a sweater. We turn on a heater. We pull the blankets up. By morning, the sun is back, and the world warms up again. We barely notice the transition. On the moon, the transition between day and night is a catastrophe that repeats every month. NASA has officially ranked surviving the lunar night as its #1 technical challenge for establishing a sustained presence on the moon. Not the radiation, not the dust, not the vacuum, the night, because everything else can be mitigated to some degree, at least for short periods. But if you cannot keep your systems running through 14 days of absolute darkness at temperatures that would freeze carbon dioxide solid, then nothing else matters. Your base is dead. Think about what happens when the sun goes down on the moon. If your habitat relies on solar panels for power, and most proposed designs do because nuclear power introduces its own enormous set of problems, then the moment the sun drops below the horizon, your power supply goes to zero. Not gradually, not like a cloudy day on Earth where you still get some diffuse light. Zero. The sun is either above the horizon, or it is not, and when it is not, there are no photons hitting your panels for 14 days. So you need batteries. Massive, heavy batteries that can store enough energy to run life support, heating, lighting, communications, air filtration, water recycling, and every other critical system for 2 solid weeks. And these batteries need to function at temperatures that would shatter most materials. Standard lithium-ion batteries, the kind that power your phone and your laptop, have a minimum operating temperature of about -40 degrees Celsius. The lunar night is 4 to 5 times colder than that. The batteries themselves would need to be kept warm, which requires energy, which the batteries are supposed to be providing. It is a circular problem that has no easy solution. The alternative is nuclear power, specifically radioisotope thermoelectric generators, which convert the heat from decaying radioactive material into electricity. These devices have been used on deep space missions for decades. They work reliably in extreme cold and do not depend on sunlight. But they use plutonium, which is extraordinarily expensive, difficult to produce, highly toxic, and politically controversial. The idea of launching large quantities of plutonium into space and landing it on the moon raises serious safety concerns. If a launch failed, and the rocket carrying the plutonium broke apart in Earth's atmosphere, the contamination could be widespread. These are not theoretical objections. They are the reason that nuclear power for space exploration remains limited and contentious. Some engineers have proposed burying habitats under a layer of regolith, using the moon's own soil as thermal insulation. Measurements and models suggest that temperatures under about 1 meter of regolith stabilize at approximately -53 degrees Celsius. That is still bitterly cold by Earth standards, but it is vastly more manageable than -180 on the exposed surface. This approach has real promise, but it introduces its own challenges. Burying a habitat means you need heavy construction equipment on the moon. It means you need to move and compact large quantities of that abrasive, toxic, electrostatically charged dust we discussed earlier. And it means that every time someone needs to go outside for maintenance or exploration, they must travel from a buried, insulated environment through an airlock to the exposed surface and back, tracking dust through the process. No human being has ever experienced the lunar night. Not one. All 6 Apollo missions that landed on the moon touched down during the early lunar morning and lifted off before nightfall. The longest any human stayed on the lunar surface was about 75 hours during Apollo 17. That is just over 3 days. They experienced lunar morning, lunar midday, and a bit of lunar afternoon. They never saw the sun set on the moon. They never felt the temperature begin its long plummet into the abyss. Every piece of human experience on the moon comes from what amounts to a pleasant morning visit. We have never tested our technology, our engineering, our biology, or our psychology against the full reality of a lunar night, and the machines we have sent have not fared well. Russia's Lunar-cognitive rover, which landed on the moon in 1973, operated successfully for about 4 months before its radioactive heater ran down and it froze to death during a lunar night. It never woke up. In early 2024, Japan's slim lander made history by surviving 3 lunar nights, but only by shutting down completely and entering a hibernation state, essentially dying temporarily and hoping that when sunlight returned, its batteries would have retained enough warmth to restart. It worked, barely, and with significant degradation to the lander's systems. That is not a viable strategy for human habitation. You cannot put a city into hibernation every 2 weeks. There are some locations on the moon, particularly near the poles, where certain elevated areas receive near constant sunlight, because the sun stays close to the horizon and illuminates peaks and crater rims, even when surrounding areas are in darkness. These so-called peaks of eternal light have been identified as prime locations for future bases precisely because they minimize the night problem. But even these locations are not perfectly illuminated. They still experience periods of darkness, and they are located in some of the most challenging terrain on the moon, on the rims of craters near the poles, where temperatures in the adjacent permanently shadowed regions plunge to near absolute zero. Living on a peak of eternal light would mean existing on a narrow strip of illumination with a frozen abyss on one side and the harsh lunar plains on the other. It is not exactly the suburban moon colony of science fiction. The lunar night represents the ultimate test of any proposed lunar settlement. It is 2 weeks of darkness, 2 weeks of extreme cold, 2 weeks of no solar power, 2 weeks of reliance on stored energy and nuclear fuel, 2 weeks of mechanical stress on every system, and 2 weeks of psychological pressure on every person. And it happens every month, forever, without exception. There is no summer on the moon where the nights get shorter. There is no seasonal relief. The cycle is as rigid and merciless as clockwork. And that brings us to perhaps the most underestimated danger of all, the one that has nothing to do with physics or chemistry or engineering, the one that lives inside the human mind. Let us talk about what it would feel like to actually live on the moon. Imagine, for a moment, that all the technical problems have been solved. The habitat is pressurized. The radiation shielding is adequate. The dust is managed. The life support systems work. The power systems can handle the lunar night. Everything functions as designed. You are safe, physically at least. But you are also on the moon. You wake up in the morning, if you can call it morning. There is no dawn. There is no bird song. There is no breeze coming through a window. The lighting in your habitat is artificial, tuned to mimic the spectrum of sunlight, but not fooling your body's ancient rhythms. You eat breakfast from sealed packages of processed food. There are no fresh eggs, no toast, no fruit from a tree. The water you drink has been recycled from your own waste products and the waste products of everyone else in the habitat. It is perfectly clean, perfectly safe, and perfectly depressing. You go about your work. Your workspace is a pressurized module roughly the size of a shipping container. The same module you work in every day. the same module your colleagues work in every day, the same handful of people you have seen every day for months. There are no strangers, no chance encounters, no new faces. The social world of a lunar base is as small and contained as a prison, except that in prison you did not volunteer, and you can count the days until release. When you are done working, you might exercise. For 2 hours, just like the astronauts on the space station, because your body is slowly deteriorating, and the exercise is the only thing keeping it from deteriorating faster. You run on a treadmill in a grey room. You lift weights on a machine designed for partial gravity. You sweat and breathe and push yourself. And when you are done, you are still on the gem moon. If you look out a window, and your habitat has one, you see the same view you have seen every day. Grey, an endless expanse of grey. Grey soil, grey rocks, grey craters, grey mountains against a black sky. There is no blue, no green, no colour at all except what humans have brought with them. The sun, when it is up, is blindingly bright against the black sky, casting razor-sharp shadows because there is no atmosphere to scatter the light. There is no twilight, no soft gradients, no golden hour, just stark, brutal contrast between blinding light and absolute shadow. And then the sun goes down, and for the next 14 days, the only light comes from the earth, if you are on the near side, and from the stars. The earth hangs in the sky like a blue marble, a fragile, beautiful, heartbreakingly distant marble. You can see the swirls of white clouds. You can see the blue of the oceans. You can see the green and brown of the continents. Everything you have ever loved, every place you have ever been, every person you have ever hugged or kissed or argued with, everyone you miss, everyone who misses you, is on that tiny blue sphere, 384,400 kilometers away. About 2.5 days by spacecraft, if you could leave, which you cannot. This is where the psychology of lunar living becomes critical and deeply troubling. The most common psychiatric issues reported during space missions are adjustment reactions, which present primarily as symptoms of anxiety and depression. These are not signs of weakness. They are normal human responses to abnormal conditions. Even the most mentally resilient people in the world, people selected and trained specifically for the rigors of space, experience psychological strain during long-duration missions. One experienced astronaut became clinically depressed at the start of a long-duration ISS mission, simply because of the isolation from his family. The Soyuz T-14 Salyut 7 mission in 1985 was abruptly terminated, and crew depression was identified as a contributing factor. Canadian astronaut David Saint-Jacques, speaking from the International Space Station, was refreshingly honest about the experience. He said, and I quote loosely here, that it can be depressing sometimes if you are not careful. This candor is remarkable because for decades, space agencies promoted an image of astronauts as superhuman, unflappable heroes who never struggled emotionally. The reality is very different. Astronauts are human beings in extreme conditions, and they experience the full range of human emotions, including fear, loneliness, sadness, frustration, and despair. Research has documented a pattern that scientists call psychological closing. Over the course of long-duration missions, crew members tend to communicate less with mission control and with people on Earth. They begin to filter what they say, withholding concerns and emotions. They become more insular, turning inward and focusing on their immediate group. Some crew members develop what researchers call autonomization, a tendency toward increased egocentrism and self-focus. Studies of International Space Station crews found a 20% increase in interpersonal problems during the second half of missions. The initial excitement and novelty wear off, the sameness sets in, and relationships that were easy in the first weeks become strained over months. On the ISS, astronauts can talk to their families in real time. There is no significant communication delay between the station and Earth. They can video call their spouses and children. They can receive care packages on resupply ships, favorite foods, personal items, letters from home. These connections are lifelines. They are the threads that keep the psyche tethered to the world below. On the Moon, the communication delay is only about 1.3 seconds each way, which is short enough for real-time conversation. This is a genuine advantage compared to a Mars mission, where the delay would be anywhere from 4 to 24 minutes, but the physical isolation is just as complete. You cannot get on a spacecraft and come home for the weekend. There are no surprise visits. There are no resupply ships arriving every few weeks with treats from home. You are there, and Earth is there, and the gap between you is a vacuum that nothing can cross quickly or easily. The confined living space is another major stressor. A lunar habitat would be small. Not small like a cozy apartment. Small like a submarine. Every sound carries. There is no privacy that is not artificially constructed. You hear your crewmates breathing, eating, typing, moving around, exercising, arguing, laughing, snoring. You develop an exquisite and often irritating awareness of every habit and quirk of the people around you. The way someone clears their throat, the way someone chews, the way someone leaves their equipment in the wrong place. On Earth, these minor annoyances are absorbed by the vastness of your social world. You see other people. You go for a walk. You change your environment. On the Moon, the annoying person is also the only person, and there is nowhere to go. Noise is an underappreciated stressor. On the International Space Station, the continuous ambient noise level is approximately 72 decibels, which is roughly equivalent to being near highway traffic. Life support systems, fans, pumps, and equipment create a constant hum that never goes away. It affects sleep quality, concentration, and mood. A lunar base would have similar background noise from its life support systems, and unlike on Earth, you cannot step outside for quiet. Outside is vacuum. Outside is death. Sleep disturbance is one of the most consistently reported problems during space missions. The lack of a natural day-night cycle means your body's circadian rhythm has nothing to anchor to. On Earth, the rising and setting of the sun sends powerful signals to your brain that regulate your sleep-wake cycle, your hormone production, your body temperature, and your mood. On the Moon, these signals are absent for 14 days at a time during the lunar night, and during the lunar day, the light is constant and harsh. Artificial lighting can mimic a normal schedule, but the body is not easily fooled. Astronauts consistently report difficulty falling asleep, frequent waking, and a general sense of fatigue that accumulates over the course of a mission. And sleep deprivation does not just make you tired, it impairs judgment, slows reaction time, increases emotional volatility, and reduces the ability to handle stress. In an environment where a single mistake can be fatal, where equipment malfunctions require clear-headed problem-solving, and where interpersonal conflicts can escalate with nowhere to escape, the cognitive effects of chronic sleep disruption are genuinely dangerous. There is a phenomenon associated with space travel that has received a great deal of popular attention, and it is worth discussing in this context. It is called the overview effect. This term was coined in 1987 to describe the cognitive shift that many astronauts experience when they see Earth from space for the first time. The experience is consistently described as profound, transformative, and deeply moving. Astronauts report a sudden and overwhelming sense of the fragility and interconnectedness of life on Earth. National borders disappear. Political conflicts seem absurd. The thin blue line of the atmosphere looks heartbreakingly delicate. Many astronauts describe a feeling of unity with all of humanity and a deep desire to protect the planet. A survey of 39 astronauts and cosmonauts found that every single one reported positive changes as a result of flying in space. The highest rated change was a stronger appreciation for Earth's beauty. From the Moon, you can see Earth clearly. It is a bright, beautiful sphere in the black sky, about 4 times the size of the full moon as seen from Earth. You can see weather patterns, ocean colors, continental outlines. It is, by all accounts, one of the most stunning sights any human being can experience. The famous Earthrise photograph, taken by Apollo 8 astronaut William Anders in 1968, showing our planet rising above the desolate lunar horizon, is widely considered one of the most important photographs in human history. It helped launch the environmental movement by showing people, for the first time, what their home looked like from the outside. But the overview effect has a darker potential that is rarely discussed. For a visitor, seeing Earth from the Moon is awe-inspiring. For a permanent resident, seeing Earth from the Moon might become something else entirely. It might become a constant reminder of everything you have lost. Every green forest, every blue ocean, every sunset, every rainstorm, every familiar face is right there, visible but unreachable. The beauty that initially inspires awe could, over time, curdle into grief. The overview effect could invert, becoming not a source of wonder, but a source of profound and unrelenting homesickness, a reminder that the only world truly suitable for human life is the one you left behind. For a permanent lunar settlement, there is no return. Not easily, not cheaply, not quickly. You are living on a world that is trying to kill you in 7 different ways, and the only world where you truly belong is hanging in the sky like a Christmas ornament you can never touch. This is the psychological reality of living on the Moon. Not the excitement of exploration, not the thrill of discovery, not the heroism of pushing the frontier. Those things are real, and they matter, and they sustain people through short missions. But for a permanent settlement, for a place where people raise children and grow old and die, the excitement fades. What remains is the sameness, the confinement, the isolation, the grey, the silence, and the blue marble in the sky that reminds you, every time you look up, of everything you are missing. So let us take a step back now and look at everything we have discussed. The vacuum, the radiation, the dust, the gravity, the night, the psychology. 6 distinct categories of danger, each one severe enough on its own to make permanent human habitation on the Moon extraordinarily difficult. But here is what makes the situation truly hopeless in a way that individual challenges do not capture. These dangers do not exist in isolation. They compound, they interact, they amplify each other in ways that are greater than the sum of their parts. Consider the interaction between radiation and dust. Cosmic rays slam into the lunar surface, and the surface responds by generating secondary radiation. That same surface is covered in dust that is electrostatically charged by the solar wind and ultraviolet radiation. When astronauts walk on the surface, they kick up this charged, irradiated dust, which clings to their suits, enters their habitats, and is inhaled into their lungs. Inside the lungs, the dust particles, which contain nanophase iron created by the same micrometeoritic impacts that form the regolith, generate reactive oxygen species that damage cells. The radiation hitting the lungs from the outside and the chemical damage from the dust hitting from the inside are a 1-2 punch that no organ was designed to withstand for extended periods. Consider the interaction between low gravity and bone loss and the vacuum. If someone living on the moon for years develops severe osteoporosis from the chronic low gravity, their bones become fragile. A fall that would be minor on Earth could cause a serious fracture on the moon. And on a lunar base, a fractured bone is not just a medical problem. It is a staffing crisis, an engineering crisis, and potentially a survival crisis. If the person with the broken bone was the one responsible for maintaining the life support system, or the one who knew how to repair the airlock seal, the entire base could be at risk. There are no hospitals on the moon. There are no ambulances. There are no replacement workers who can arrive in a few hours. Consider the interaction between the lunar night and psychology. For 14 days, the base is in darkness. Solar power is unavailable. The inhabitants are relying entirely on stored energy, which means conservation mode. Lights are dimmer. Heating is reduced to save power. Non-essential systems are shut down. The habitat feels colder, darker, and more claustrophobic than during the lunar day. And everyone knows that if the power storage system fails during those 14 days, there is no backup. There is no calling for help that can arrive in time. The awareness of that vulnerability, the knowledge that you are 14 days from sunlight and entirely dependent on machines that are being stressed by extreme cold, would create a persistent background anxiety that would intensify with each passing night cycle. Consider the interaction between dust and engineering and the vacuum. The dust degrades seals. The vacuum means that any degraded seal is a potential leak point. A leak in a pressurized habitat on the moon is not a slow, manageable problem, the way a draft in a house on Earth might be. Depending on the size of the breach, it could depressurize a section of the habitat within minutes or hours. The dust that caused the seal failure is also the dust that contaminates the air filtration system, meaning that the system designed to keep the air clean is simultaneously under attack from the same substance that is threatening the structural integrity of the habitat. You are fighting the same enemy on two fronts with the same resources. And consider the cumulative effect of all of these stressors on the human mind over years and decades. You are living in a confined space. You are eating recycled food. You are breathing recycled air. You are exercising out of medical necessity rather than joy. You are watching your bone density slowly decline despite your best efforts. You are exposed to a constant background of radiation that you cannot see or feel, but that you know is accumulating damage in your cells. You are managing interpersonal relationships with the same small group of people you have been managing for years, with all the accumulated grudges and irritations that implies. You are watching the blue earth hang in the sky, beautiful and unreachable. And every 29 days, the sun goes down for 2 weeks, and you sit in the dark, hoping the power holds, hoping the seals hold, hoping you hold. This is not a life. This is a survival exercise. And the human mind is not designed for permanent survival mode. It needs rest. It needs variety. It needs beauty. It needs surprise. It needs the random encounter, the unexpected kindness, the serendipitous discovery. It needs the full spectrum of human experience, from boredom to excitement, from solitude to community, from the mundane to the transcendent. A lunar base can provide some of these things some of the time, but it cannot provide all of them all of the time. And over the course of a lifetime, those gaps add up. They become voids. And voids have a way of being filled with despair. Let us also talk about something that the popular imagination often glosses over when it envisions moon bases, the basic resources of life: water, food, air. These three things are so abundant on Earth that we barely think about them. We turn on a tap and water flows. We walk into a store and buy food. We breathe without effort or thought. On the moon, every molecule of water, every calorie of food, and every breath of air must be manufactured, recycled, or shipped from Earth at staggering expense. Water is perhaps the most critical resource. The human body needs about 2 liters of drinking water per day, plus additional water for hygiene and food preparation. On a lunar base, water would need to be recycled with extraordinary efficiency. Every drop of sweat, every exhalation, every trip to the bathroom would need to be captured and processed back into clean water. The International Space Station already does this, and its water recycling system is remarkably effective, recovering about 98% of all water, including urine and humidity from the air. But that 2% loss must be replaced. On the ISS, replacement water arrives on resupply ships. On the Moon, resupply from Earth would be prohibitively expensive for a large settlement. There is a potential local source. Scientists have confirmed that water ice exists in the permanently shadowed craters near the Moon's poles, the same regions where temperatures plunge to near absolute zero. This ice could theoretically be mined and processed into usable water, but extracting water from shadowed craters that are among the coldest places in the solar system and transporting it to a habitat located somewhere more hospitable would require heavy equipment, significant energy, and constant maintenance, all in an environment where dust clogs everything and extreme temperatures stress every component. It is doable in theory. It is brutally difficult in practice. Food presents an even more daunting challenge. You cannot farm on the Moon in any traditional sense. There is no soil. Lunar regolith is toxic to most plants because it contains heavy metals and lacks the organic matter and microbial communities that make Earth soil fertile. Experiments have shown that some plants can technically grow in lunar regolith if it is extensively treated, but the yields are poor and the process is complex. Hydroponic systems, where plants grow in nutrient-rich water solutions, are more promising, but they require water, nutrients, energy for lighting, careful temperature control, and constant monitoring. A hydroponic farm large enough to feed a lunar settlement would be a massive facility that consumes enormous amounts of energy and water, both of which are precious resources on the Moon. The caloric requirements are significant. An average adult needs roughly 2,000 to 2,500 calories per day. A physically active person in a stressful environment, which describes every person on a lunar base, needs more. Growing all those calories locally would require greenhouse facilities far larger than any that have been proposed or tested for space applications. The reality is that for the foreseeable future, a lunar base would depend heavily on food shipped from Earth, supplemented by whatever can be grown locally, and food from Earth is expensive to launch. Estimates vary, but the cost of delivering 1 kilogram of payload to the lunar surface is typically quoted in the range of tens of thousands of dollars to over $100,000. A year's worth of food for one person weighs roughly 700 to 1,000 kilograms. The math is not encouraging. Air is another essential that must be manufactured. The habitat's atmosphere would need to be a breathable mixture of nitrogen and oxygen, maintained at comfortable temperature and humidity. Oxygen can potentially be extracted from lunar regolith which is rich in oxygen-bearing minerals, or from water ice if it can be mined. Several proposed processes could crack water molecules into hydrogen and oxygen through electrolysis, or could use high-temperature chemical reactions to extract oxygen from the metal oxides in the regolith. These processes work in laboratory settings and could potentially be scaled up. But they require energy, equipment, and maintenance, all of which are constrained on the Moon. And the air must not only be produced but also continuously cleaned. Carbon dioxide must be scrubbed. Trace contaminants from equipment, humans, and infiltrating dust must be filtered. The air system is not something you build and forget. It is a living machine that requires constant attention. The interconnectedness of all these resource challenges creates a fragility that is hard to overstate. If the water recycling system fails, you cannot make food or oxygen. If the power system fails, you cannot run the water recycler, the air scrubber, or the temperature controls. If the dust infiltrates the air filtration system, the air quality degrades, which affects health, which reduces work capacity, which slows repairs, which allows more dust infiltration. Every system depends on every other system, and a failure in any one link of the chain cascades through the entire settlement. On Earth, we are buffered by redundancy on a planetary scale. If your local water treatment plant breaks down, you can truck in water from elsewhere. If a power plant goes offline, the grid redistributes energy from other sources. If your food supply is disrupted, you drive to a different store or a different town. On the Moon, there is no elsewhere. There is the base, and there is the vacuum. There are no neighbors to help. There is no emergency backup provided by nature. The settlement is an island of life in an ocean of death, and the ocean is always pressing in. Let us also consider something that science fiction almost never addresses. What about children? If we are talking about a permanent human home on the Moon, we are talking about people being born there, growing up there, and we have absolutely no data on what 1/6 gravity does to a developing human body. We know what full gravity does, obviously, and we have some limited data on what microgravity does to adult bodies. But the effects of reduced gravity on a growing fetus, on a developing skeleton, on a maturing brain, on the complex hormonal cascades that guide a child from infancy through adolescence, these are complete unknowns. Would a child born on the Moon develop normal bones? At 1/6 g, the skeletal system would receive drastically reduced loading during the critical years of growth, when bones are establishing their density and architecture. Would those bones ever be strong enough to support the child if they traveled to Earth? Or would lunar-born humans be permanently trapped on the Moon, unable to visit the planet of their species' origin, because their bodies were too fragile to withstand Earth gravity? Would lunar-born children develop normal cardiovascular systems? Would their hearts be strong enough, their blood vessels robust enough, to handle the 6-fold increase in gravitational stress that a trip to Earth would impose? Would their muscles develop properly? Would their proprioception, their sense of where their body is in space, be calibrated correctly? We do not know. And these are not trivial questions. They are questions about whether a second generation of lunar settlers would be biologically imprisoned on the Moon, unable to ever experience the world that their parents left behind. There is also the question of reproduction itself. Studies on the effects of radiation on reproductive cells suggest that the cumulative radiation exposure on the Moon could lead to increased rates of genetic mutations in sperm and egg cells. This could manifest as higher rates of infertility, miscarriage, or birth defects. Animal studies have shown that radiation exposure can cause heritable genetic damage, meaning that the effects are not limited to the exposed individual, but can be passed down to subsequent generations. A permanent lunar population might face a slow accumulation of genetic damage that becomes more pronounced with each generation, a kind of biological decay driven by the relentless radiation bombardment that the Moon's missing magnetic field allows. These are not speculative nightmares. These are reasonable extrapolations from known science. We know that radiation damages DNA. We know that reduced gravity alters bone and muscle development. We know that dust causes respiratory disease. We know that isolation affects mental health. The only unknown is the precise magnitude of these effects over the timescales that permanent settlement implies. And the only way to find out those magnitudes would be to expose real human beings to those conditions for years and decades and see what happens. That is not science. That is experimentation on humans. And the ethical implications of that are profound. There is yet another dimension to this problem that is often overlooked, and it has to do with the very thing that makes us want to go to the Moon in the first place. Our curiosity, our ambition, our drive to explore and expand. These are beautiful qualities. They have taken our species from caves to cathedrals, from rafts to rockets. But they can also lead us astray when they are not tempered by honest assessment of reality. The dream of colonizing the Moon is seductive because it plays into some of our deepest narratives. The frontier, the new world, the brave settlers who tame the wilderness. These stories are woven into the cultural DNA of many societies, and they carry enormous emotional power. But the Moon is not a frontier in any meaningful sense. A frontier implies a wild place that can be domesticated. The American West had air, water, soil, and sunlight. It had trees and animals and rivers. It was hostile, but it was also fundamentally alive. The Moon is not hostile because it is wild. It is hostile because it is dead. You cannot tame a dead world. You can only build a bubble inside it and hope the bubble holds. And that distinction matters enormously. Because when we talk about the Moon as a potential home, we are not talking about settling a new land. We are talking about something much more radical. We are talking about creating a completely artificial environment, a closed system that provides everything a human body and mind need, and maintaining that system perfectly, without interruption, against constant entropic pressure, for the rest of time. That is not settlement. That is life support. And there is a world of difference between the two. There is another way to think about the radiation problem that makes it feel less abstract and more personal. Imagine you could see radiation. Imagine that every galactic cosmic ray that passed through your body left a tiny glowing trail, like a firefly drawing a line through the air. On Earth, you would see very few of these trails, perhaps 1 or 2 per minute, faint and distant, most of them blocked by the atmosphere and the magnetic field above you. They would be rare enough to be beautiful, little sparks of cosmic energy, harmless and fleeting. On the Moon, the fireflies would be everywhere, hundreds of them per minute, coming from every direction, passing through the walls of your habitat, through your furniture, through your crewmates, and through you. Some of them would be heavy ions, iron nuclei, and carbon nuclei moving so fast that their trails would be thick and bright, each one depositing a concentrated burst of energy along its path. Others would be protons, lighter and faster, leaving thinner trails but appearing in much greater numbers. And from below, scattered particles from the regolith would rise up through the floor like tiny geysers of light, secondary neutrons and protons kicked up by the cosmic rays that struck the ground outside. If you could see all of this, you would never feel safe on the moon. Not for a moment. The invisible would become visible, and the visible would be terrifying. You would see your own body being pierced continuously by particles that carry the energy of exploding stars. You would watch those particles pass through your heart, your liver, your brain, your reproductive organs, and you would know, with visceral certainty, that each passage carries a small but real probability of triggering the cellular malfunction that we call cancer, or the vascular damage that leads to heart disease, or the neurological change that affects cognition and memory. This is not science fiction. This is simply the reality of radiation on the moon made visible. The only reason we do not think about it constantly is that radiation is invisible. We cannot see it, smell it, taste it, or feel it. It does its work in silence, at the molecular level, inside our cells, where no human sense can detect it. And that invisibility is in some ways the most dangerous thing about it. Because what we cannot see, we tend to ignore. And what we ignore, we tend to underestimate. The neurological effects of space radiation are among the most recently studied and the most concerning. Research conducted on animal models has shown that exposure to heavy ion radiation, the kind that makes up the most damaging component of galactic cosmic rays, can cause measurable changes in brain function. Mice exposed to doses equivalent to what a lunar resident might receive showed decreased cognitive flexibility, impaired spatial memory, and increased anxiety-like behaviors. The radiation appeared to damage the synaptic connections between neurons and trigger chronic neuroinflammation, a low-grade immune response in the brain that persisted long after the radiation exposure ended. In one particularly striking set of experiments, researchers at the University of California found that mice exposed to charged particle radiation showed reduced performance on tests that required them to recognize novel objects and navigate new environments. These are the rodent equivalents of the cognitive tasks that a lunar base crew member would need to perform constantly. Recognizing when equipment is malfunctioning, navigating emergency procedures, adapting to unexpected situations. If radiation exposure degrades these abilities over time, the safety implications for a lunar settlement are profound. The very danger that threatens the crew also erodes their capacity to respond to danger. It is a feedback loop with no obvious exit. Human data on the neurological effects of deep space radiation remains limited because so few humans have been exposed to it. But what data exists is concerning. Some Apollo astronauts reported cognitive changes after their missions, including difficulty with concentration and memory. These reports were largely anecdotal and were not systematically studied at the time, in part because the culture of the astronaut corps discouraged reporting weakness of any kind. More recent studies of astronauts returning from long-duration ISS missions have documented measurable changes in brain structure, including alterations in white matter integrity and shifts in cerebral spinal fluid distribution. These changes occur even within the partial protection of Earth's magnetosphere. On the Moon, without that protection, the neurological effects would likely be more severe. There is also a phenomenon that researchers call the Mars problem, which applies equally to the Moon. In any environment where reaction time, decision-making, and cognitive clarity are essential for survival, any factor that degrades these abilities becomes a systemic risk. On Earth, if you are having a foggy day, you can stay home, rest, and recover. On the Moon, if the life support alarm sounds at 3 in the morning, and you are the engineer on duty, your cognitive state is not optional. it is mission critical. And if that cognitive state has been subtly but steadily degraded by years of radiation exposure and chronic sleep disruption and psychological strain, and the low-grade inflammation caused by inhaled dust particles, the margin for error shrinks to a razor's edge. This convergence of degrading factors is perhaps the most important thing to understand about the Moon as a potential home. No single danger is necessarily fatal on its own. The vacuum can be contained, the radiation can be partially shielded, the dust can be somewhat managed, the gravity cannot be changed, but exercise can slow the deterioration. The night can be survived with adequate power systems. The psychological strain can be mitigated with good support. But when all of these factors act simultaneously over years and decades on the same human bodies and the same human minds, the cumulative effect is not the sum of the parts. It is something worse. It is a slow, systemic erosion of health, capability, and resilience that no single intervention can fully address. Think of it this way. If you had a car that had slightly worn brakes, slightly bald tires, a slightly misaligned steering column, a slightly cracked windshield, and a slightly underpowered engine, each of those problems individually might not prevent you from driving safely. But all of them together, on a dark night, on an icy road, with no breakdown service available, would make that car a death trap. The Moon presents exactly this kind of compounding risk to the human body and mind. Every system is slightly degraded. Every margin is slightly reduced. And when something goes wrong, as it inevitably will over the course of years, the combined degradation of all those systems determines whether you survive or you do not. Engineers call this concept the Swiss cheese model of failure. Imagine multiple slices of Swiss cheese stacked together. Each slice has holes in different places. As long as the holes do not align, the stack is solid. But if enough slices shift and enough holes line up, something can pass straight through all the layers. On the Moon, each environmental hazard is a slice of cheese. Each mitigation strategy plugs some of the holes, but not all. Over time, as systems degrade and humans weaken, the holes get bigger and more numerous. And eventually, a path opens up through all the layers. That path is catastrophe. This is not pessimism. This is engineering reality. It is the same kind of analysis that informs the design of nuclear power plants, commercial aircraft, and deep-sea drilling platforms. The difference is that on Earth, when catastrophe strikes, there are external systems to respond. Fire departments, hospitals, rescue teams, supply chains. On the Moon, there are none of these things. The settlement is on its own. And the more time passes, the more degraded its defenses become, and the more likely it is that a path through all those layers of Swiss cheese will eventually open. This does not mean that short-term missions to the Moon are not worthwhile. They absolutely are. A 2-week mission operates with fresh equipment, healthy crew, full supplies, and minimal cumulative degradation. The Swiss cheese slices are thick and the holes are small. A 2-year rotation pushes those margins significantly. A 20-year settlement pushes them to the breaking point. And a permanent multi-generational colony pushes them beyond any reasonable expectation of sustained safety. The Moon's challenges exist on a spectrum of time. In the short term, they are manageable. In the medium term, they are dangerous. In the long term, they may be insurmountable. And it is the long term that the word home implies. Now let us go deeper into the radiation story, because there is a dimension to it that deserves more attention. And it has to do with something happening right now, as the Artemis program prepares to send astronauts back to the Moon for the first time in more than 50 years. When NASA designed the Apollo missions in the 1960s, radiation was a known concern, but the missions were so short that the cumulative exposure was considered acceptable. The average Apollo astronaut received a radiation dose of roughly a few millisieverts during their trip, depending on the specifics of their mission profile. That sounds small, and for a brief visit, it was. But even that small dose left its mark, as the cardiovascular mortality data revealed decades later. The Artemis missions will be longer. The initial missions plan for stays on the lunar surface lasting days to weeks. Later missions aim for stays of months, and the long-term vision includes a sustained human presence at a base camp near the lunar south pole. With each increase in duration, the radiation exposure climbs, and unlike many dangers that have thresholds, radiation damage follows, what scientists call a linear no-threshold model. This means that any amount of radiation exposure carries some risk. There is no dose below which you are completely safe. Every cosmic ray that passes through your body rolls the dice one more time. On the lunar surface, the annual radiation dose from galactic cosmic rays alone is estimated at roughly 300 to 400 millisieverts. That is about 6 times the annual occupational limit for radiation workers on Earth, and about 150 times the average annual background radiation that a person receives from natural sources on our planet. Add to that the possibility of one or more solar particle events during the year, each of which could deliver an additional acute dose of anywhere from tens to thousands of millisieverts, depending on the severity of the event and the quality of available shielding, and the numbers become genuinely alarming. NASA's current career radiation exposure limit for astronauts is designed to keep the risk of exposure-induced cancer death below 3%, with 95% confidence. For a lunar base, maintaining compliance with this limit would be extraordinarily difficult for stays longer than a few months. Some calculations suggest that without dramatic improvements in radiation shielding, a 2-year tour on the lunar surface would push astronauts near or beyond these limits, and that is just for cancer risk. The cardiovascular effects, the neurological effects, and the other degenerative changes we discussed are not even factored into that limit in a comprehensive way, because we do not yet have enough data to quantify them precisely. The prospect of shielding a habitat against radiation on the Moon has generated some creative engineering proposals. One approach is to bury the habitat under several meters of regolith, which would provide substantial shielding against both galactic cosmic rays and solar particle events. Regolith contains hydrogen, carbon, and oxygen atoms, and hydrogen in particular is effective at absorbing neutrons and reducing secondary radiation. A few meters of packed regolith overhead could reduce radiation exposure significantly, though not eliminate it entirely. Another approach involves using water as a shield. Water is rich in hydrogen and is an excellent radiation absorber. A habitat surrounded by tanks of water could provide meaningful protection. Some designs propose using the settlement's water supply itself as a structural shielding element, placing water storage tanks in the walls and ceiling of the habitat. This dual-use approach is elegant in theory, but it adds mass, complexity, and vulnerability. A breach in a water shield wall would be both a radiation crisis and a flooding emergency. Magnetic shielding has also been proposed. The idea of creating an artificial magnetic field around a habitat to deflect charged particles the way Earth's magnetosphere does. This concept is scientifically sound in principle, but remains far from practical implementation. The energy requirements for generating a field strong enough to meaningfully deflect galactic cosmic rays would be enormous, and the technology is still in early experimental stages. It is a long-term aspiration, not a near-term solution. The reality is that any lunar base in the foreseeable future will have to accept a significant level of radiation exposure for its inhabitants. That exposure will be managed, reduced where possible, and monitored carefully, but it will not be eliminated. And for stays of years or decades, the cumulative biological effects remain deeply uncertain. Let us return for a moment to the dust, because there is one aspect of its behavior that we have not yet explored, and that makes it uniquely maddening from an engineering perspective: the electrostatic charge. On Earth, static charge dissipates easily. Humidity in the air provides pathways for charge to leak away. Grounding wires and conductive surfaces further reduce static buildup. On the Moon, there is no humidity. There is no conductive atmosphere. The vacuum is one of the best electrical insulators in existence. So when lunar dust particles acquire a charge from solar ultraviolet light and the solar wind, that charge stays indefinitely. The particles remain sticky with electric force for as long as they exist, which on the Moon, where nothing weathers or erodes or dissolves, means forever. This has consequences that go beyond the simple annoyance of dust clinging to spacesuits. Electrically charged dust behaves strangely. Near the terminator, the boundary between day and night on the lunar surface, strong electric fields develop as the transition between sunlit charged surface and dark uncharged surface creates voltage gradients. These fields can actually levitate dust particles, lifting them off the surface and suspending them in a thin cloud that extends several meters or even kilometers above the ground. Apollo astronauts observed evidence of this phenomenon, describing what they called bands, streamers, and twilight rays near the horizon during lunar sunrise and sunset. This means that on the Moon, the dust does not just sit passively on the surface waiting to be kicked up. It is actively propelled into the space above the surface by electrostatic forces. A habitat near the terminator region could be subjected to a constant drizzle of electrostatically levitated dust particles, coating solar panels, clogging sensors, degrading optical instruments, and infiltrating any equipment that is not perfectly sealed. And as we have discussed, perfect sealing on the Moon is an aspiration, not an achievement. The Apollo astronauts also noticed something else about the dust that troubled the engineers. It was almost impossible to brush off. The nylon bristle brushes they used to clean their suits removed the larger particles, but left behind a fine layer that was essentially bonded to the fabric by electrostatic forces. Vacuum cleaners had limited success. Wet wipes worked somewhat, but water is a precious resource that cannot be used liberally for cleaning. Later missions experimented with different cleaning approaches, but none were fully effective. After each moonwalk, the astronauts returned to their lunar module trailing clouds of fine dust that contaminated every surface inside. For a permanent base with daily outside excursions, this contamination problem would compound continuously. Every airlock cycle introduces more dust. Every suit cleaning attempt removes some, but leaves residual particles. Over weeks and months, the interior surfaces of the habitat would accumulate a fine layer of abrasive, electrostatically charged, chemically reactive, potentially toxic dust. Air filtration systems would be the first line of defense, but filters clog. They need to be replaced. And where do the replacement filters come from? They either need to be manufactured on the Moon, using local materials and processes that do not yet exist, or shipped from Earth at tremendous expense. There is a certain Sisyphean quality to the dust problem. you can never win. You can only keep fighting day after day forever, knowing that the dust will outlast your patience, your equipment, and your supply of replacement parts. It is the kind of slow, grinding, relentless challenge that breaks systems and breaks people, not through catastrophe, but through attrition. Let us think more about what long-duration isolation actually does to the mind, because the research from Earth-based analogues provides some sobering data. In 2020 and 2021, 2 participants spent 61 days inside the lunar habitat in northern Greenland, a facility designed to simulate conditions on a lunar base. The habitat was small, remote, and surrounded by an inhospitable Arctic landscape. The 2 men reported a range of psychological experiences over the course of their stay. One consistently reported more negative emotions than the other, and felt that time was passing abnormally slowly. The other felt time was passing faster than normal. Both experienced periods of low mood and frustration. Physical exercise, leisure activities, and conversations unrelated to mission tasks were identified as the most effective mood boosters. The researchers noted that the participants might not experience the same degree of negative consequences as people in truly involuntary isolation, like prisoners, because they had voluntarily signed up and knew there was an end date. But they also noted clear potential for negative psychological effects, even in a volunteer scenario. And their study had a sample size of 2, which limits how much we can generalize. But the finding that even 2 motivated volunteers in a simulated lunar habitat for just 2 months experienced significant mood fluctuations and psychological strain is worth taking seriously. Larger studies of space analog environments, including the Mars 500 experiment in Russia, where 6 volunteers were sealed in a mock spacecraft for 520 days, have found similar patterns. Crew cohesion tends to deteriorate over time. Interpersonal conflicts increase. Communication with the outside world becomes less frequent and less open. Some crew members develop displacement behaviors, directing frustration and hostility outward toward mission control, rather than addressing conflicts within the group. Others become withdrawn and disengaged. These findings align with research on isolated groups in other extreme environments, including Antarctic research stations, submarine crews, and remote military outposts. The pattern is remarkably consistent across different settings and cultures. Isolation and confinement, sustained over months, tend to produce a predictable arc of psychological change. Initial excitement and bonding give way to routine and minor irritations, which compound into significant interpersonal tensions, which can eventually fracture group cohesion and individual morale. Strong leadership, structured schedules, access to private space, and meaningful connection with the outside world can mitigate these effects, but they cannot eliminate them. On a lunar base, the isolation would be more extreme than in any of these analog environments. The nearest help is hundreds of thousands of kilometers away. The landscape outside the windows is entirely alien. There are no seasonal changes, no weather events, no wildlife sightings, no unexpected visitors, none of the random stimuli that keep the human brain engaged and alert. The monotony would be absolute. And monotony is not just boring. Researchers have identified it as a genuine psychological hazard, linked to reduced cognitive performance, increased risk-taking behavior, and a phenomenon called asthenization, a gradual loss of drive, energy, and emotional resilience. The circadian rhythm disruption deserves special attention because it is one of those problems that sounds minor, but cascades into everything. Your circadian rhythm is not just about when you feel sleepy. It regulates hormone production, immune function, body temperature, digestion, mood, and cognitive performance. It is one of the most fundamental biological rhythms in the human body, and it is calibrated to the approximately 24-hour cycle of light and darkness on Earth. On the Moon, the natural light-dark cycle is 29.5 days long. Your body's clock has no external reference point that matches its internal rhythm. Artificial lighting can simulate a 24-hour cycle, and this is what the ISS uses. But studies have shown that artificial lighting is a poor substitute for natural sunlight. Astronauts on the ISS consistently report sleep problems, and these problems worsen over the course of long missions. On the Moon, during the 14-day night, the absence of any natural light whatsoever would remove even the subtle cues that artificial lighting tries to replicate. The psychological weight of 2 weeks of unbroken darkness should not be underestimated. On Earth, even in the Arctic during polar night, there is still some reflected light from snow, some aurora, some sense of atmospheric depth. On the Moon, during the night, outside the habitat, there is nothing but starlight and the ghostly glow of Earthshine. Inside the habitat, there is only the artificial light that you and your crewmates have chosen to turn on. The darkness outside is not the darkness of a cloudy night in the countryside. It is the darkness of the void, and knowing that the void extends in every direction around you, that there is nothing between you and the stars except a thin wall of metal and composite material, that the only light and warmth in your world is what you create and maintain yourself. That knowledge presses on the mind like a weight that never lifts. Let us consider, too, the question of purpose. Human beings need meaning. We need to feel that our lives matter, that our work contributes to something larger than ourselves, that the sacrifices we make are worthwhile. On Earth, meaning is woven into the fabric of daily life. We raise children. We care for aging parents. We contribute to communities. We create art. We build relationships. We participate in the messy, glorious, exhausting business of civilization. On a lunar base, the primary purpose of most activity would be survival. Keeping the systems running, maintaining the habitat, growing food, recycling water, monitoring radiation levels, repairing equipment, conducting scientific research when time and energy allow. For the first crew, and perhaps the second and third, the novelty of being on the Moon would provide its own sense of meaning. They are pioneers. They are making history. Every task, no matter how mundane, is the first time that task has been done on the Moon. But for the 10th crew, the 20th, the 100th, what is the narrative then? You are the 14th person to replace the air filtration membrane this year. You are running the same soil analysis that has been run 10,000 times before. You are eating the same hydroponic lettuce that everyone has been eating for years. The heroic narrative fades, the routine sets in, and without a deep and sustainable source of meaning, routine becomes drudgery, and drudgery becomes despair. This is not a criticism of the people who would live on the Moon. It is a recognition of a fundamental human need that the lunar environment cannot easily satisfy. We are social creatures who evolved in rich, varied, stimulating environments. We need novelty, nature, diversity, and the unpredictable rhythms of a living world. The Moon can provide none of these things. It can provide silence, beauty of a stark and alien kind, and the profound experience of seeing Earth from the outside. These are valuable, but they are not enough to sustain a human life across decades. Not for most people, not without a toll. If you are still awake, listening, Letting these ideas wash over you, consider this final thought. The moon is not our enemy. It is not cruel. It is not malicious. It is simply indifferent. It does not care whether we come or go, whether we succeed or fail, whether we live or die on its surface. It is a ball of rock and dust and ancient shadow, and it has been exactly what it is for 4.5 billion years. It was here before life on Earth began, and it will be here long after the last human has drawn their final breath. Our dreams of colonizing it, of making it a second home, of transforming its grey face into something familiar and welcoming. These are our dreams, not its. And the moon owes us nothing, but we owe ourselves the truth. And the truth is that the moon will never be a human home. Not because we are not brave enough, not because we are not clever enough, but because the moon is not alive enough. Home requires life, real life, breathing, growing, changing, unpredictable, messy, beautiful life. And the moon has none of that to offer. What it does offer is perspective. The cold, clear, uncompromising perspective of a dead world looking back at a living one. And in that perspective, there is a gift more valuable than any colony. The gift of knowing, truly knowing, in our bones and in our hearts, that the blue sphere hanging in the black sky above the lunar horizon is the only home we have, the only home we need, and perhaps the only home we will ever deserve. So hold that image as you close your eyes tonight. The blue sphere, the swirling clouds, the shimmer of oceans, the thin, miraculous, impossibly thin line of atmosphere that keeps everything alive. Hold it gently, because it is everything. It is all of us. And the moon, in its eternal silver, silence, is the one thing in the sky that never lets us forget it. So if the moon is this deadly, this inhospitable, this fundamentally unsuited to human life, why do we keep talking about going back? Why do space agencies around the world continue to plan lunar missions? Why do billions of dollars flow toward programs like Artemis and similar efforts by China, Europe, and private companies? Are all these brilliant scientists and engineers delusional? No, they are not. And this is where the story takes its most important turn. Because the answer to why we keep going back to the moon is not that we think we can turn it into a home. The answer is that the moon is something much more valuable than a home. It is a laboratory. It is a training ground. It is a proving ground. And it is a stepping stone. The distinction matters. A home is a place where you live permanently, where you build a community, where you raise families, where you put down roots and expect to stay for generations. A laboratory is a place where you go to learn. A training ground is a place where you prepare for something harder. A stepping stone is a place that takes you somewhere further. The moon can be all three of these things, but it cannot be a home. And the sooner we are honest about that distinction, the better our plans for the future of space exploration will become. Think about what the moon offers as a laboratory. It is a natural vacuum chamber 3,400 kilometers in diameter. It is a radiation environment that we need to understand before we send humans to Mars or beyond. It is a place where we can study the long-term effects of partial gravity on human physiology in ways that are impossible on Earth or on the space station. It is a geological archive that contains records of the solar system's history going back 4.5 billion years. Records that have been erased on Earth by plate tectonics and weathering. The permanently shadowed craters at the poles may contain water ice that has been there for billions of years. Ice that could tell us about the history of water in the inner solar system and potentially about the delivery of ingredients for life. These are scientific treasures of incalculable value. They justify sending humans to the moon for weeks or months at a time, with all the expense and risk that entails. Think about what the moon offers as a training ground. If we ever want to send humans to Mars, which is a journey of 6 to 9 months each way through deep space radiation, followed by an extended stay on a planet with a thin atmosphere, a toxic surface, and its own gravity and dust challenges, we need practice. We need to test our habitats, our life support systems, our power systems, our medical procedures, our psychological support strategies, and our emergency protocols in an environment that is harsh but close to home. The moon is only 3 days away by spacecraft. If something goes wrong on a lunar base, evacuation to Earth is at least theoretically possible. If something goes wrong on Mars, the crew is on their own for months. The moon gives us a place to make mistakes, learn from them, and improve our technology and procedures before we attempt the much longer, much more dangerous journey to Mars. Think about what the moon offers as a stepping stone. The moon's gravity is weak enough that launching spacecraft from its surface requires far less energy than launching from Earth. If we could establish fuel production facilities on the moon, extracting oxygen and potentially hydrogen from lunar ice and regolith, the moon could serve as a refueling station for missions deeper into the solar system. This concept, sometimes called a lunar gateway, has been a staple of space exploration planning for decades. The idea is not to live on the moon permanently, but to use the moon as a platform from which to reach further. There is also the matter of what we can learn about ourselves. Every challenge the moon throws at us teaches us something about human biology, human psychology, human engineering, and human resilience. The bone loss that occurs in reduced gravity has direct implications for treating osteoporosis on Earth. The radiation protection strategies developed for the moon will benefit cancer patients receiving radiation therapy. The water recycling systems designed for space are already being adapted for use in water-scarce regions on Earth. The psychological research conducted on isolated crews has applications for understanding and treating depression, anxiety, and social dysfunction in Earth-bound populations. The moon does not have to be a home to be useful. It does not have to be livable to be worth visiting. But there is a deeper philosophical point here that goes beyond utility, and it has to do with the nature of home itself. What makes Earth our home is not just that we evolved here. It is that Earth is alive. Not just biologically alive, though it is that too, with its forests and oceans and bacteria and fungi and insects and birds and whales and all the billions of organisms that make up the biosphere. Earth is also geologically alive. Its core churns. Its continents drift. Its volcanoes erupt and create new land. Its water cycle moves moisture from ocean to cloud to rain to river and back to ocean. Its atmosphere breathes, cycling oxygen and carbon dioxide through plants and animals in a rhythm that has persisted for billions of years. The moon is none of these things. It is geologically dead. Its core solidified long ago. Its volcanoes have been silent for over 1 billion years. There is no water cycle. There is no carbon cycle. There is no nutrient cycle. There are no ecosystems. There is rock, dust, vacuum, and radiation. The moon is not sleeping. It is not dormant. It is not waiting to be awakened. It is dead in the most fundamental sense of the word. And a dead world cannot become a home for a living species, not without turning that world into something it is not. Not without essentially bringing Earth with you and reconstructing it, molecule by molecule, inside a bubble on an alien surface. And at that point, the question becomes, Why not just stay on the planet that already provides all of these things for free? This is not a defeatist argument. It is not a counsel of despair. It is a plea for honesty. The moon is magnificent. It is worthy of study, worthy of exploration, worthy of admiration. It has shaped Earth's tides, stabilized our planet's axial tilt, and inspired every civilization in human history. Our species has a deep and ancient relationship with the moon, and that relationship will only deepen as we continue to explore it. But exploration and habitation are not the same thing. Understanding a place and living in a place are not the same thing. And pretending otherwise does a disservice both to the moon and to ourselves. Let us also consider the timeline of the dangers we have discussed. Many of the threats the moon poses are not immediately fatal. They are slow. They are cumulative. They are insidious. Radiation damage accumulates over years and manifests as cancer or cardiovascular disease decades later. Bone loss progresses month by month, becoming critical only after long exposure. Dust-related lung disease develops slowly, with symptoms worsening over years of exposure. Psychological strain builds gradually, like water behind a dam, until one day the structure fails. These are not dangers that will stop a 1-week visit or even a 1-month research mission. They are dangers that make a 1-year stay risky, a 5-year stay dangerous, and a lifetime stay potentially devastating. And this temporal dimension is crucial because it creates a false sense of security. The first astronauts who return to the moon under the Artemis program will probably be fine. They will spend a few days or perhaps a few weeks on the surface. They will encounter the dust and be annoyed by it. They will receive some radiation and not feel any effects. They will experience the low gravity and find it exhilarating. They will look out at the grey landscape and the blue earth and feel wonder. They will come home and be celebrated, and rightly so, and their success will be interpreted by the public and by policymakers as evidence that the moon is habitable, that the challenges are manageable, that a permanent base is feasible. But the real test will not come for years. It will come when the 3rd or 4th rotation of crew members starts to show higher rates of eye problems. When the annual bone density scans reveal losses that exercise cannot reverse. When the air filtration logs show a gradual increase in dust, particle counts, despite continuous maintenance. When the psychological evaluations reveal increasing rates of depression and interpersonal conflict. When someone develops a cough that does not go away. When the seals on the main airlock need to be replaced for the 4th time in 3 years because the dust has worn them beyond tolerance. When the power storage system degrades to the point where surviving the lunar night requires shutting down half the base. These will be quiet crises, not dramatic explosions or catastrophic failures, just a slow, steady erosion of health, equipment, and morale. The kind of erosion that doesn't make headlines but makes life increasingly difficult and dangerous. The kind of erosion that eventually forces a painful question. Is this sustainable? And the honest answer, based on everything we know about the moon's environment and the human body's response to it, is probably no. Not with current technology, not with foreseeable technology, not as a home. But perhaps that is okay. Perhaps we do not need the moon to be a home. Perhaps the moon's greatest gift to our species is not as a place to live, but as a mirror that shows us, with crystalline clarity, exactly how perfectly suited we are to the planet we already have. Every danger on the moon is really a lesson about Earth. The vacuum teaches us the value of atmosphere. The radiation teaches us the value of our magnetic shield. The dust teaches us the value of rain and wind and water that smooth the rough edges of the world. The low gravity teaches us the value of weight, of the constant pull that keeps our bones strong and our hearts resilient. The night teaches us the value of an atmosphere that distributes heat, that softens transitions, that turns the terror of darkness into the gentle rhythm of evening and morning. And the isolation teaches us the value of the 7 billion other humans we share this planet with, the strangers and friends and family members who make our world feel inhabited and alive. Every time we look at the moon and see a potential home, we are, in a sense, looking past it. We are looking past the real lesson it has to offer, which is that home is right here. Home is this extraordinary, improbable, irreplaceable planet that provides everything we need without us having to lift a finger. Air, water, food, warmth, light, a magnetic shield, a thick atmosphere, a living biosphere that recycles our waste, produces our oxygen, grows our food, and heals itself from almost any damage we inflict. We have been given, through no merit of our own, the single most habitable place in the known universe. And the moon, in its silent, silver, unlivable way, is constantly reminding us of that fact. There is a quietness to the moon that is worth sitting with for a moment. If you were standing on the surface right now, in a spacesuit, with nothing but the hiss of your breathing system and the gentle whir of your air circulation fan, you would experience a silence more profound than anything available on Earth. There is no wind on the moon, no rustling leaves, no distant traffic, no birdsong, no thunder, no ocean waves, no cricket chirps, no children laughing, no dogs barking, no music from a neighbor's window, nothing. Just the silence of a world where sound cannot travel because there is no medium to carry it. If you set down a speaker on the lunar surface and played your favorite song at maximum volume, you would hear nothing. The vibrations would die in the vacuum before they traveled an inch from the speaker cone. That silence is not peaceful. It is not meditative. It is not the comfortable silence of a library or a meditation retreat. It is the silence of absence, the silence of a world where the conditions for life, and therefore for the sounds of life, simply do not exist. It is the most honest thing about the moon. It tells you the truth without embellishment. This is not your place. You are a visitor here. You are welcome to look, to study, to wonder, to learn. But you cannot stay. And maybe that is the most beautiful thing about the moon after all. Its honesty, its refusal to pretend. Earth is a complicated world. It flatters us. It indulges us. It absorbs our mistakes and heals from our messes, at least for now. It makes life so easy that we forget how extraordinary life is. The moon offers no such flattery. It shows us, with stark and unforgiving clarity, exactly what a world without life looks like. And in doing so, it makes the world with life seem all the more precious. There is a famous quote from the astronomer Carl Sagan, who looked at a photograph of Earth taken by the Voyager, one spacecraft, from a distance of 6 billion kilometers. In that photograph, Earth appears as a tiny pale blue dot, barely a pixel in a sunbeam. Sagan reflected on that image and said that it showed that our planet is a lonely speck in the great enveloping cosmic dark. He urged us to deal more kindly with one another and to preserve and cherish this pale blue dot, the only home we have ever known. From the moon, Earth is not a dot. It is a sphere, a vibrant, colorful, cloud-swirled sphere that glows with life in a way that no other object in the sky does. And that sphere, not the grey expanse of the lunar surface beneath your feet, is the real prize. That sphere is where our future lies, not because we lack the courage or the cleverness to live elsewhere, but because the universe, in its infinite indifference, gave us exactly one world where we belong, and the moon, in its dead and silent way, will forever remind us of that truth. So the next time you look up at the moon, do not see a future colony. Do not see real estate. Do not see humanity's next address. See what it really is: a teacher, a mirror, a laboratory, a stepping stone, a beautiful, barren, brutally honest world that shows us, better than anything else in the sky, why the Earth is the most precious object in the known universe. The moon will never be a human home, and that is not a failure. That is a lesson. Let that thought settle in as you drift off tonight. Let the image of the moon wash over you, silver and serene in the darkness above. Let the knowledge of its dangers and its beauty coexist in your mind like light and shadow on the lunar surface. And let the quiet understanding take root that the greatest adventure in space may not be leaving Earth at all. It may be learning, truly and deeply learning, to appreciate the miracle of the world we already have. If you enjoyed this journey through the science of the moon, take a moment to press that like button. It helps more people find this kind of content. And if you are not already subscribed, consider joining us. We take these long, slow, deeply researched trips through the cosmos regularly, and there is always room for one more traveler. Leave a comment and tell us where you are listening from tonight, what time it is where you are, and whether the moon is visible from your window. We love reading those. Every comment is a little connection point between all of us, scattered across the surface of the one world that truly belongs to us. Thank you for spending this time with us. Thank you for your curiosity. Thank you for letting the science settle in at whatever pace feels right. Whether you absorbed every detail or drifted off somewhere along the way. Either way, we are glad you were here. Sleep well, fellow traveler. And next time you see the moon, give it a nod of respect. It earned it. We all did. Because the hardest lessons are the ones that teach us what we already have. Good night. If you made it here, you already know what this feels like. That quiet, that drift. But every night it ends. The video stops. The silence wakes you. And you're reaching for your phone at 3 a.m., choosing something new when all you wanted was to stay asleep. Beyond the Stars was made for that moment. 5 deep sleep experiences, hours long, no ads, no endings, just the night, all the way through. Yours tonight for a one-time purchase. Begin now at mycosmicdrift.com.